Alright, this is Electrostatics 6. It's our next step, and we're going to do the crazy integration thing, this time for a thin ring of charge. And we'll look at what that means for a circular arc. So, what we're going after is, for that ring of charge, at a point on axis, what the electric field is from everything. So, same idea we've been doing. Let's take our ring of charge and start looking at, why is this just not behaving? Let's take our ring of charge and start looking at how we're going to get the electric field from it. So the first thing we're going to do is take a tiny piece of charge dq and see what the electric field from that is. So at point P, that points away, assuming it's positively charged. We have a little differential piece of our electric field, but we know on the other side of that ring there's another dq. It gives me another contribution to my electric field. It's going to cancel out that y contribution. It's going to be that way all across the ring. So really all that we're going to be interested in is the dE cosine theta part, just the x part of it because of symmetry. So looking at this, our electric field E is going to be all of the little electric fields added together times the cosine of theta. So let's plug in what we know. Our differential form of the electric field is k dq over r squared times the cosine of theta. So let's look at what all these things mean. K obviously is a constant, that'll be coming out. What is r? R is the distance between my differential piece of charge and point P. Well, we know looking at it that r squared is going to be, in this case, b squared plus a squared. And as we go around to different points on our ring, it's not going to change the value for A, and it's not going to change the value for B. So R is going to be a constant. Let's look at cosine theta. Now, we know that cosine theta, if this is my angle right here, is based on everything we have there. It's just B, that x value, over R. Well, R is not going to change as I go to different points on my ring, and neither is B. So looking at this, K, R squared, and cosine theta are all constants that can come out of the integration. So my electric field is K times cosine theta over R squared on the integral of dq. Now, when we integrate just dq, that gives me my total charge q. So I've got kq times cosine theta over r squared. But those aren't my given quantities. I need to substitute this stuff in there. So my electric field, we're going to need some room, is kq over b squared plus a squared times the cosine of theta, which is b over b squared plus a squared to the 1/2. Because that's what R is. So when we simplify that, our electric field is KQB over B squared plus A squared to the 3/2. That's my function for the electric field from my ring of charge. It's as simple as that. So that's the first thing that we're going to do with this. I'm going to go ahead and write that up here at the top. E is equal to KQB over A squared plus B squared. That whole quantity is to the 3/2. What we're going to look at next is finding, for this ring of charge, potential, which should be easier. Looking at the potential, we know that from one little piece. I'm going to have a dV here. I don't have to worry about anything like substitution. All it really depends on is how much charge I have, which is dq times the r, how far away I am. So getting our potential, dV is going to be equal to k dq over r, where we know that r is equal to root a squared plus b squared. Now, looking at this, k doesn't change for every piece of dq, and r doesn't change either. That stays the same. So my voltage is k over r on the integral of dq. So the voltage here will just be kq over r, or for what we have, kq over a squared plus b squared to the 1/2. That's all we have to do to get the voltage of this charge distribution. This is an easy one to deal with, but we're going to have to memorize both of these things. V equals kq over a squared plus b squared to the 1/2. We're going to have to memorize both of these things for what we do in the next video when we look at a disk of charge. So we'll come back to that, but this is all for now.